How do we put the right amount in the right place? Atom by atom. Welcome to deposition, the first major step in a chip's life. Every chip starts with a blank wafer, but it doesn't stay blank for long. The first thing we do is put down a layer. Deposition means laying down a thin film on the wafer. Sometimes it's a metal, sometimes an insulator, sometimes a single layer of atoms. The films are nanometers thick, a few dozen atoms across. Too thick, the device is wrong. Too thin, the device is wrong. The margin is measured in atoms. Think of it like spray painting the wafer, except the paint is invisible. The surface has to stay mirror flat, and a thickness mistake of a few atoms scraps the wafer. Real fabs don't use one deposition method. They use 6. Each one has a different job. First, physical vapor deposition. Heat a target until atoms fly off and land on the wafer. Best for metals, copper, aluminum, titanium barriers. Second, chemical vapor deposition. Pump reactive gases above the wafer. They leave a coating behind. Best for dielectrics and polysilicon, the insulators and structural films inside a chip. Third, atomic layer deposition. Pulse one chemical, purge. Pulse another, purge. 1 atomic layer per cycle. Slow, but precise to the atom. Best for ultra-thin critical layers, like gate oxides, where every atom matters. Fourth, plating. Wafer goes in a liquid bath. Current flows. Copper plates onto the surface. Best for bulk copper, filling the big interconnect features fast and cheap. Fifth, epitaxy. Grow a single crystal layer that aligns perfectly with the silicon underneath. Best for crystalline films, like the silicon germanium channels inside a modern transistor. Sixth, spin-on dielectric. Drip a liquid precursor. Spin the wafer fast. The liquid spreads into a thin uniform coating, then cures into a solid. Best for planar layers, flattening and low-K dielectrics. 6 methods. 6 jobs. A modern chip uses all of them at different stages of the build, but every one of them faces the same question. The question is, how do we know it's correct? Did the film land at the right thickness? The right uniformity across the wafer? The right composition? Without a measurement, you don't know. And in a fab, don't know is the same as failed. Every step has a check, every layer has a measurement, every wafer has a digital trail. To find out, engineers reach for different tools at different times. 2 tiers. Tier 1 runs in line on every single wafer. Ellipsometry, bounce polarized light off the surface. The polarization shift gives thickness. Mapped across the wafer, it gives uniformity, subatomic layer resolution. 4-point probe. For metal films, push current through 2 pins, measure voltage across the other 2. You get sheet resistance, a direct read on whether the metal landed right. Fast, cheap, every wafer. Tier 2 runs when you're qualifying a recipe or chasing a yield excursion. Sampled, not every wafer. X-ray reflectometry, glancing X-rays off the film. Density, thickness, roughness. The structure of the layer, not just its size. SEM cross-section, paired with EDS. Look at the layer with electrons. EDS reads out what the film is made of, element by element. And for the thinnest layers, the ALD films a few atoms thick, 2 separate instruments. TEM, the transmission electron microscope. Electrons pass straight through a slice of the wafer, resolving individual atomic layers. XPS, X-ray photoelectron spectroscopy. X-rays knock electrons off the surface. Their energies tell you what atoms are there, and what they're bonded to. Different physics, same purpose, atomic scale truth for the thinnest films. Different cadences, same question, is the layer right? A wafer in production doesn't move on a single check. It clears 5 gates. 1. Metrology at spec. 2. SPC in control. 3. Defectivity below spec. 4. Tool health current. 5. Engineer sign-off for any excursion. All 5 green, the lot moves. 1 red, It waits. This lesson focused on gate 1. The other 4 are just as real and just as critical. Each floor of the chip has its own blueprint. How do we draw it? Perfectly. Every time. Next up, lithography. If you work in a fab, here's what this looks like on Tuesday morning. A process engineer pulls the latest ellipsometer data from every wafer batch on the deposition tool. The data lands in JUMP, plotted as an SPC chart, with Western electric rules running in the background. The moment a rule trips, say a clear upward drift in the data, the tool goes down inside 5 minutes. Why so fast? Every minute of unplanned downtime on a 300mm fab tool is roughly $5,000. Calibration logs get pulled, recipe history gets checked. The engineer asks, did the film land at spec, or are we drifting? The deposition recipe lives or dies on CPK, Process Capability Index.